Well, welcome everybody, and thanks for joining this session on dealing with Chlor Alkali and Mercury, looking for synergies between Minamata and Stockholm Convention, with the presentation of some practical cases in that vein. First, I'd like to introduce myself. My name is Benjamin Vauter. I work with the United States Environmental Protection Agency in the Office of International Affairs, where I am an international mercury policy specialist. And so my role, I support facilitating the global implementation of the Minamata Convention on Mercury. And in that role, I am a co-lead for the UNEP Global Mercury Partnerships Chlor Alkali Partnership Area, along with my other co-lead from UNIDO. And so it's in that function as co-lead for the Global Mercury Partnership Chlor Alkali Partnership Area that I'm here today, co-chairing this session with Guido, and I will also be giving the first presentation. So let's get this going. Again, I introduced myself, so I'll just move past that. So first, the way I'm going to run this, I'm going to give a quick intro to the Minamata Convention, just briefly. You'll probably be hearing a lot about that, so I don't want to give you too much history of the Global Mercury Partnership. And then I'll highlight some articles of the convention that pertain to the Chlor Alkali industry and the partnership areas of the Global Mercury Partnership. And finally, I'm going to summarize how the partnership plans to help reduce mercury consumption and supply related to the Chlor Alkali sector moving forward. So the Minamata Convention entered into force in 2017. It addresses supply, trade, use, release, and emission of mercury, environmentally sound storage and disposal, and strategies to address contaminated sites. There are provisions for technical assistance, capacity building, information exchange, public awareness, research, and monitoring. And there are reporting requirements for each party to the convention that they need to submit to the Secretariat to ensure or to track the measures taken to implement the convention. So here's a map that shows kind of the distribution of parties that have joined the convention. We have 140 parties to the convention today, and 128 signatories to the convention. So the history of the Global Mercury Partnership is kind of outlined here. Maybe a bit confusing of a diagram, but the idea is essentially that the work of the Global Mercury partnership started as the UNEP Mercury program, started with the Global Mercury Assessment in 2002, which formed the basis for the work of the UNEP Global Mercury Partnership. The Global Mercury Partnership was initiated in 2005. UNEP Governing Council decisions have consistently recognized the work of the partnership leading up to negotiations of the convention. The partnership provided technical briefings at the INCs and contributed to government's better understanding of issues around mercury. And so the partnership contributed to the completion of the text of the Minamata Convention at INC 5 and continues to support implementation of the convention today. So there are 8 partnership areas, each with their own business plans under the Global Mercury Partnership. You can see them listed out here. One of the partnership areas is the Chlor Alkali Partnership. There's a website for the Global Mercury Partnership and each partnership area has its own page. And there you can find the individual business plans for each partnership area, which outlines in detail the approaches and the strategies for the partnership area in reducing or eliminating or managing mercury within that partnership area. Currently, there are over 200 partners of the Global Mercury Partnership, which include governments, international organizations, NGOs, industry, academia, and others. And so the mandate for the Global Mercury Partnership is really to deliver immediate action. This was before the Minamata Convention was in force. While it was still being negotiated, there was an understanding that there needed to be some action on mercury, and the Global Mercury Partnership provided that support before the Minamata Convention came into force. Now that the convention is in force, the partnership is sort of evolving. Presently evolving to kind of establish its new identity, and which is really supporting the implementation of the convention now that the convention is in place. And so it works kind of in parallel to the Minamata Convention. So some of the activities that the partnership has delivered is generation of baseline data and information, guidance materials and toolkits, information gathering and exchange, advocacy and awareness raising is a big one. Strengthening national policies to identify problems and take strategic actions, and it supports demonstration projects. I don't know, this may show up as a blank screen. It kind of looks like that now. I think it's just for presentation mode, but the point of this screen was, it was just kind of a diagram. Oh, here it is. This diagram shows how the partnership contributes to the implementation of the convention. If you look at the second column, it refers to mercury and chlor alkali, and then down on the left are articles in the Minamata Convention that the Chlor Alkali Partnership area addresses. And so I'll get into these in more detail on the next slides. So the first one was Article 3 on mercury supply sources and trade, which restricts export of mercury and restricts import of mercury from non-parties. There are requirements again for reporting under Article 21. And so I guess on this slide, again, Article 3, paragraph 5, parties are supposed to identify stocks of mercury that exceed 50 tons and sources of mercury that are generating mercury stocks exceeding 10 tons that are located within its territory. Now this applies to chlor alkali sector because chlor alkali is one of, in present day, those facilities have, the ones that still have mercury cells in them, are carrying and holding some of the largest stocks of mercury that we're needing to manage around the globe. And so parties are identifying often chlor-alkali facilities that have 50 metric tons or 10 metric tons of mercury on site, and then so we work to try to help them to manage those stocks as they move toward decommissioning or closing their chlor-alkali facilities. Article 3 also specifically mentions decommissioning of chlor-alkali facilities and requires that mercury is disposed of from these facilities in an environmentally sound manner, which is covered, mercury waste is covered in Article 11. And so paragraph 3A of Article 11, it specifically calls out the Basel Convention technical guidelines on the environmentally sound management of waste consisting of containing or contaminated with mercury or mercury compounds. And these are the guidelines that are recommended for waste management under the convention. And the Minamata COP right now is currently developing a list of waste that are to be managed in this way. Article 5, it identifies manufacturing processes that are addressed under the convention, specifically a phase out date for processes that are listed in Annex B, which I'll get to on the next slide. So Annex B here identifies chlor-alkali production and gives a phase-out date for mercury cells and chlor-alkali production by 2025. Presently, mercury use in chlor-alkali is still an allowable use under the convention up until 2025. Countries may submit a request for an exemption from this phase-out date, or an extension really to the phase-out date, which could extend phase-out until 2035. Europe has done a great job of getting rid of most of the mercury, if not all of the mercury cell chlor-alkali facilities on the continent, and so now is kind of looking more at the, as many of you probably know, the management of contaminated sites, and then also management of the stocks of mercury that may still be held on site. So if a facility is listed in Annex B, countries are supposed to take measures to address the emissions and releases from the facilities, report on measures taken to reduce emissions and releases from facilities, and then identify facilities that would be qualified under Annex B, and then report on them to the Minamata Secretariat, who should be making that information publicly available for anybody to see. Article 14, this is more specific to like where the Global Mercury Partnership is supported by the convention. This article relates to capacity building, technical assistance, and technology transfer. Says that capacity building technical assistance may be delivered through partnerships, including partnerships involving the private sector. Cooperation and coordination with other multilateral environmental agreements in the field of chemicals and waste should be sought to increase the effectiveness of technical assistance and its delivery. And I chose to pull out this specific paragraph from the article because it calls out cooperation, coordination with other multilateral environmental agreements. So this is language in the Minamata Convention that basically spurs us to work more closely with folks working in, for example, the Stockholm Convention. And I think that's something that, for me personally, I'm looking forward to learning more about how we could work together as part of this session. Global mercury consumption has decreased in the chlor-alkali sector, as you can see on the left, the yellow line, the yellow-orange line, and then in the table on the right. So there's been a steady decrease in demand from the chlor-alkali sector over the last 10, 20, 5 years. So as that's happening, there's still the threats of mercury from chlor-alkali facilities getting into other sectors, specifically artisanal small-scale gold mining, which is the leading source of mercury use these days and is often illicit, illegal, or informal. And so the U.S. and the EU have created mercury export bans to reduce the availability of the residual mercury from the chlor-alkali sector. In both the EU and the US, mercury recovered from chlor-alkali must be stabilized, stored, or disposed domestically or locally. If converted into a stable compound, export is allowed for disposal. And oftentimes export is the only option due to limited local regional disposal options, especially in lower income economies. And this is something that we really run into a lot, is the issue of local and regional storage, short-term or interim storage of mercury in a lot of countries is non-existent, and waste disposal is non-existent. So oftentimes the mercury waste is being exported often to Europe for final disposal. So the final slide here is some of the priority actions of the chlor-alkali partnership area. We're moving into the future to play a more active facilitative role in addressing and working more closely with non-World Chlorine Council facilities and their associated governments, assist in identifying remaining mercury facility status and needs, we need to, as a partnership area, and actually I would ask anyone's assistance who's listening to this now, assistance in developing a global inventory of mercury cell chlor-alkali facilities. We've done one in the past, but it's probably about maybe 10 years old now. We really need to update that to be more accurate. And so assist in identifying and accessing technical and financial resources to support conversion, decommissioning. This process is really expensive. Again, lower income economies that don't have the resources of the US and Europe are struggling to figure out exactly how they're going to decommission and convert, and then even further struggling to understand how they're going to manage the contaminated sites that are left over, which we know can be an expensive undertaking. Identify viable interim and long-term storage and final disposal solutions, again, as I was mentioning earlier. And then cross-partnership collaboration within the Global Mercury Partnership. So we just recently, last week, held a webinar with the Waste Management Partnership area, which went really well. And so we'll be looking to hold more of those types of webinars and expand collaboration across the partnership areas. And then finally, we'd like to explore and identify synergies with other multilateral environmental agreements like the BRS conventions and I put in GCF Green Climate Fund here just because converting from mercury cell to membrane cell technologies in chlor-alkali industry is a big energy saver, and so there may be some ways to kind of tap into Green Climate Fund resources to support some of these conversions that we're trying to get creative about financing. So that's it for me. Thanks for your attention. This is my email address here if you'd like to contact me. I left the webpage for the Global Mercury Partnership there. And yeah, please feel free to email. I'm sorry I'm not there in person to talk after the fact, but I think Guido will continue to guide us in the right direction.
What option do you have for the final disposal of pure mercury?
Right now it's being sent to salt mines in Germany. Has been pretty much where most of the world is sending their mercury for final disposal. And so generally you would stabilize the mercury into mercury sulfide is a common practice. So it's a solid element so that it won't be so mobile in the environment, and then you just bury it.
Okay, thank you.
So maybe shortly introduce to myself, Roland Weber, mainly working on persistent organic pollutants, not on Minamata. Yes. So John asked me if I could say something on the synergy between Minamata and the Stockholm Convention. So that's part of the presentation. And as presentation topic, I choose the relevance of mercury contaminated sites for global mercury release and the implementation synergy of the Minamata and the Stockholm Convention. When we look to the short history of mercury, the whole thing started already 3,500 years ago, where in Egypt and China, they used mercury for religious and health effects in Greek, afterwards for ornaments, cosmetics in Egypt. And already in the 8th century, when the Japanese put gold on their big Buddha in Nara, they had a big mercury contamination. They found that the workers are intoxicated and the palace had to be closed for some time. And you can look into current research. There is research around these sites and the mercury contamination. Since 1800, we have also industrial uses. And it took more than 150 years to find out that around these industrial uses, there can be large pollution of the environment and contamination of the people. And the first one was found 1956 in Minamata, where the people got ill, the cats got ill, the fish got ill. And that's also a reason Japan took the responsibility and took it as a Minamata Convention. Then in 2002, UNEP started a global mercury assessment, and it took 15 years that we had the first conference of parties of the Minamata Convention in 2017. In addition, what Ben has said, the Minamata Convention has various elements of mercury contaminated sites, one under Article 11 on waste and one own Article 12 on contaminated sites. So here the treaty calls on parties to endeavor to take action to address contaminated sites and encourage parties to cooperate in the formulation of strategies and the execution of activities to identify measures, classify depending on priorities of contaminated sites, and manage and as appropriate remediate contaminated sites. And there's a very nice review article of Kochman, and he estimated the total emissions from contaminated sites. Here to the air emissions between 70 to nearly 100 tons, while another review article estimated more than 2,000 tons of mercury release from contaminated sites globally. Also, another assessment for the releases to rivers and estuaries. So Kochman here estimated between 60 to 160 tons a year. And the other paper from Sunderland, they estimated between 1,000 to 2,700 tons. So this means that the total emission from contaminated sites could be up to 50% of total mercury release from the contaminated sites, and from the estuaries and rivers also about 8 to 50% of releases stem from the contaminated sites compared to industrial releases. And when we look to the total historic accumulation from contaminated sites, Kochman estimated that we have between 50,000 to 100,000 tons of mercury released over these last 3,500 years of mercury use. So therefore, we have huge reservoirs, which are probably the most important future mercury sources, especially when we address better the artisanal mercury and so on, and when the chlor-alkali reduce, then the mercury sites, contaminated sites, will be the main driver. What are the major contaminated site sources? We just have to go the life cycle of mercury. We have the mining sites of mercury and some other mining sites. We have the formal use in the manufacturing of products like pesticides, medical devices, light bulbs and heads. And around these facilities, you have also mercury contamination. We have contaminated sites from the use in industry, like the chlor-alkali site, the acetaldehyde production, vinyl acetate, and also PVC production, but it is only the specific PVC process which is using acetylene. So there you have a mercury catalyst with high release. Then application and storage, disposal sites of mercury pesticides, gold, precious metal mining, including the artisanal gold mining, which currently is the main source to the atmosphere. Sites of mercury recycling, non-ferrous metal processing, disposal sites of mercury, and at the end also graveyards with all our amalgam. Kochman also made nice overview global maps where you see here primary mercury mining we mainly had in North America, China, yeah, some in Europe, and also some in Spain. So one of the largest one is in Spain. Then chlor-alkali plants, we know where they are. You see also Europe is a big hub for chlor-alkali plants. Large-scale precious mining sites, North America, South America, bit in Europe. And also other industrial sites. Here the non-chlor-alkali industrial sites for acetaldehyde, vinyl acetate, PVC, and oil refineries. And here one of them, this is Minamata, where they had acetaldehyde production and polluted the area there. Also, there is estimate of historic releases for the primary mercury mining, for chlor-alkali, and for the large-scale precious mining. For the chlor-alkali industry, it is estimated that in history, chlor-alkali has released between 1,400 tons to 3,700 tons of mercury at the sites. So often you have it in the soil. Maybe you will show afterwards. I will show another example. Then when we look to the primary mercury mining, it is estimated that we have 10,000 tons of release at the primary mining sites. And the largest amount has been used in the large-scale precious metal production. Here the estimate for North America is about 61,000 tons, used, for example, in California, and even more has been used in South America with an estimate to close to 200,000 tons from this study. But you saw Kochman, he estimated that the total amount is 100,000 tons. So there are also still some dispute of scientists, but let's say that's a factor of 2. I give you one example, and where you see how the Minamata Convention mercury pollution links with the POP pollution. So that's the release and the contamination of a Finnish river, Kemijoki, with mercury from a factory which had a chlor-alkali production between 1940 to 1984. And they also produce pentachlorophenol and some other things. And so they have released about 30 tons of mercury into that river. And over the last 80 years, mercury have moved through the river, maybe 50 kilometers long, and most of it, 28 tons, have already released the Gulf of Finland and are in the Baltic Sea and are going into the fishes there. And also for this river, there was a complete estimate of dioxin release from that factory, because that factory have had pentachlorophenol production with large side production of dioxins, and also some minor release from chlor-alkali process. So what you see here for the dioxins, most of the dioxins are still in the sediments, so it moves slower compared to the mercury, and about 50% have reached the Gulf of Finland. And in the Baltic Sea, you might know the fish are still not marketable in Europe in respect to dioxins and PCB limits. Yeah, but that's only one of that sources. But you see here in the assessment and also in the release that we have at these sites where you have chlor-alkali, also organochlorine production sometimes, with large amounts of dioxins, and therefore here we can do an assessment of both types of convention relevant pollutants. And the chlor-alkali production itself with graphite electrodes, so have produced dioxins. They were operated between 1890 and 1980s. So therefore, at some of these sites, we have a large dioxin contamination. And other chlor-alkali technologies like the mercury or membrane or diaphragm technologies, they have significantly less dioxin releases, but they have either mercury releases or the membrane can also have releases of PFAS. Yeah, I have read it in a report on these chlor-alkali sites, but I have not seen real data. So here I would be quite interested. Just here, one of our studies where we assessed chlor-alkali sites for pollutants in Germany and in Japan. And you see that at these soils, we not only have the dioxins and furans, but we have chlorinated naphthalines, chlorinated phenanthranes, the whole zoo, and a detailed assessment in respect to risk is needed. We also have an overview where these old chlor-alkali sites are here in Europe. That's a map from 1910, and you see for the different sites which one has used this Griesheim process with the graphite electrode, or which one has used the mercury. And for these individual chlor-alkali site plants, it would need to be assessed what have been the history, because some have used for sometimes graphite electrodes, for sometimes the mercury process. So you can have also both contaminants at these sites. And there are 2 reports on global chlor-alkali and chlorine production. So therefore, we have a quite good overview on all the chlor-alkali processes in the world, yeah, and could then see what kind of productions has been operated at these different sites, and what kind of assessment of POPs we will need to do. And Guido will do it at least for one site. Conclusions. Mercury contaminated sites considerably contribute to environmental pollution and release of mercury, likely becoming the most important source in future. Major sites are mercury mining sites, mercury in manufacturing, mercury in industry use, application storage, and the gold mining. And chlor-alkali production sites can also be contaminated with both POPs, unintentional POPs, and mercury. So when assessing chlor-alkali production sites, also the technology used in the past need to be assessed, including the management of waste. The historic assessment should also evaluate the past production portfolio at the individual sites, including pesticides or organochlorine chemicals with large formation and releases of dioxins and furans. And here we have the nice synergy between the Minamata and the Stockholm Convention. Yeah, thank you for your attention.
Yes, the floor is yours, Nikola.
Hello, everyone. My name is Nikola Jelinek, and I am from Arnica Toxics and Waste Program, which is an IPEN hub for Eastern, Western, and Central Europe. IPEN is an international pollutants elimination network consists of more than 600 organizations and from more than 125 countries. And my paper is about mercury contamination as a legacy of chemical production in the CEE region. Minamata Convention was adopted in 2013 to reduce transport of mercury globally. But some of the processes still use mercury or mercury compounds. Between them, there is mercury-based chlor-alkali production with phase-out in 2025, sodium and potassium methylate or ethylate production, vinyl chloride monomer acetaldehyde and polyurethane production also. This paper is focused on 8 case studies and its contamination with mercury. It focuses on former or recent chemical factories, and some of them got remediated, but they remain contaminated. It's about CEE and CIS countries. Its focus is on fish, and it's based on previous larger report. Localization of case studies is mainly Europe. Yes. First 2 are in Czech Republic, and the third one is in Germany. I will be focused on these 3 because I don't have that much time. The 4th one is in Slovakia. 5th one is in Romania. Number 6 and 7 are in Kazakhstan, and the last one is in Albania. I hope we all agree on that the concentration of mercury in sediment corresponds with the concentration of mercury in fish. And here is an overview of my case studies and concentration in sediments. I will be talking about those 2, and you can see that the highest concentration measured here is in a chemical complex in Pavlodar, which is in Kazakhstan. It's 1,500 milligrams per kilogram. So to the first case. First case study is Spolchemie in Ústí nad Labem. I am from Czech Republic, that's why I chose those I knew best. So this one is on the north of Bohemia, located near Labe River, which is the biggest river in Czech Republic. And I found really beautiful photo of this chemical complex in Ústí nad Labem. It's one of the Chlor Alkali production plant in Czech Republic and one of the oldest also in Czech Republic. So the green star means the Spolchemie. There is River Bílina, which flows into the biggest river of Czech Republic, River Labe. In this box, you can see the thresholds for mercury in fish for the human consumption, and those orange ones exceed those limits from United States EPA, and those red ones exceeded the limit from World Health Organization. Unfortunately, we don't have samples from fish samples from River Bílina, but we have the concentration of mercury in biofilm and sediment. But if you follow the river and you want to go fishing nearby the Spolchemie, your catched fishes exceed those limits from United States EPA. But if you go downstream, they exceed also the limits from WHO. And if you cross the border with Germany, they exceed it as well. Next one is Splana Neratovice. Those who know Czech Republic knows that this here is located Prague, the main city of Czech Republic. So it's like 20 kilometers away. And the area of Splana Neratovice consists of those beautiful buildings. And between those buildings, there was measured concentration of mercury in soil, which varied between 1,500 to 2,700 milligrams per kilogram, but up to 37,000 milligrams per kilogram. It is located near it's the same river as before. It's Labe, the biggest river in Czech Republic, and this is the longest one. But the concentration in this river also exceeds, in all of those cases, the limit from WHO. And there is also one quarry which is separate from the river, and but the concentration of mercury in fishes also exceed those limits. This is my favorite picture. It's Splana Neratovice, and concentration of mercury interpolated in oak bark nearby. So you can see that it's more than 0.55 micrograms per kilogram in oak bark. And another interesting chart. There is a value 28.79 nanograms per cubic meter, and it's for Libiš. Libiš is part of Neratovice, where is also Splana Neratovice located, but it's twice as high as in Ostrava, which is the most industrially loaded region in Czech Republic. And the last one is it's Marktredwitz chemical factory, located here nearby the border with Czech Republic, but in Germany. This is the oldest chemical factory in the world, and I chose it because I was born here. Let's take a closer look. The green star is the factory. Nearby is Preslava River. Unfortunately, we don't have data for fish, but we have for sediments and water. And you can see that during the flood, the concentration in sediments is twice as high as at normal conditions, but the concentration in water is 6 times as high. The Reslava River then goes to the river Ohře, which goes to the river Labe, which is the biggest river in Czech Republic, and on the Ohře River is Skalka Reservoir, and the concentration of mercury in sediment is 12.9 milligrams per kilogram. But the problem is the volume. There is almost 500,000 of cubic meters of it. And the concentration of mercury in fish also exceed the higher and also the lower limit. I was talking only about Neratovice, Ústí nad Labem, which is the Spolchemie, Marktredwitz, but you can see that the same problem is in Slovakia, in Romania, in Kazakhstan, and in Albania. All of these samples, its mean levels of mercury in muscle, they all exceed the limits from United States EPA and also from World Health Organization. So we could see that the long-lasting use of mercury on sites leads to exceeding limits in fish for human consumption, and those cases demonstrate that they contaminate as well as its own area as well as outside. And some of the sites mentioned were remediated, but they are still contaminating fish from sediments, for example, in Skalka, or you could see that the concentration in oak bark is really high. And there is observed simultaneous contamination by POPs in some cases. And IPEN developed basic guidance for identification, management, and remediation of these contaminated sites. And its previous version included basic technologies also for POP-contaminated sites. And this document became basis for development of guidance to the Minamata Convention. And there is one important thing, that this document does not suggest waste incineration of waste with POPs and mercury, but indirect thermal desorption as the most suitable way for mercury and POPs. That's everything. Thank you for your attention.
You mentioned in one of your slides that you analyzed the biofilm. What is that?
Biofilm is the if you have stone and you put it in water, then something grows on it, and it's biofilm. It's microorganisms.
And that's where you also find the higher mercury.
Yeah, but it was actually not our data. It was from some other study.
Okay, thank you. Any other questions?
Maybe more of a comment. So the factory that you were presenting, located in Germany, we found it also in connection with production of pesticides containing HCH while compiling our inventory with Germany. And we know that the focus for this site was on the mercury. The site itself was remediated and cleaned up. But of course, there's still this problem with the remaining mercury in the creeks and rivers. With the mercury. And to my knowledge, there's no solution to that yet. And Germany and the Czech Republic are debating about it. We shall take care of it.
It was for the Skalka Reservoir was for recreation, but in my life I couldn't swim there because they said it's hazardous. Okay, thank you.
Where Stockholm meets Minamata, mercury and HCH issues at Chlor Alkali facilities. So it's great to be here and to be able to speak. Just about myself, I'm Guido van the Coterlet. I'm a consultant, contaminated sites and hazardous wastes. I've been working for TAO for 17 years and experience in training and field work at contaminated sites and working with hazardous waste. So I see a lot of POPs, I see a lot of pesticides and mercury. TAO, of course, we have one of our former CEOs here actually who's still actively involved, and we have actually the CEO of TAO Spain. So we are, as a company, very much involved in the POPs business and mercury business for many years, and we are a proud sponsor of the forum. So I wanted to tell that to you. I don't want to go into much about these slides. We've already had it 2-3 times. We know that there is synergies between the Minamata and the Stockholm conventions, and we know that basically they'll have the same goal and relevant actions. And what we see from our different projects is we encounter both the mercury problem and the HCH problem at a number of these locations. So yeah, why does it happen? Well, Chlor Alkali facilities and HCH, mercury cell technology. So when we're talking about Chlor Alkali facilities, you have different types. And only one of them is actually mercury based. But it was the main technology until around 1972 when a decline set in. And that was mostly to do with the whole Minamata scandal coming up. The overall process at these mercury cell facilities consisted of bringing a saturated brine, so basically salt water, I'd say, into an elongated, slightly inclined through between shallow co-current streams of mercury and assembly of electrodes, either graphite or metal. And during the production of this caustic soda, which was the main thing, you had also chlorine, and that is needed for HCH production. So essentially, you know, it was logical for a lot of these facilities to also invest in the actual creation of HCH or of chlorinated pesticides. So we all know that to produce HCH, because that's what we're talking about mostly at the forum, it's basically photochlorinating benzene, and if you do that, you create a product called technical HCH, which is about 14% lindane, and the rest, 86%, is inactive isomers. And so the other isomers at most of these locations, especially the older ones, because back in the days, in the 40s and 50s, they would actually use technical HCH on the fields, but it stinks. It stinks, your potatoes smell like it, your grain smells like it. So only after around the 1950s did they start to use lindane. And that's when the real waste problem showed up, because 1 in 8. So you got 1 ton of lindane, you got 8 tons of rubbish. So what we see at the sites is we've got the huge quantities of waste dumped everywhere. But what we also see is that the graphite anodes in the mercury cells, they would wore down and they needed to be replaced. And some of the parts are actually into the mercury. And so these graphite anodes can have really high mercury concentrations. I think you've seen them also in all his, George, the little black things. But they can be also a source of dioxins. Although on paper a closed system, a mercury cell is on paper a closed system, you see that the site loses several tons of mercury a year. That's through evaporation, that's through your brine sludges, that's through your wastewater. On average, a Chlor Alkali facility would lose around 2 tons a year just through their solids. I'm not even talking about the evaporation. What we also see at the sites is PCB and asbestos. PCB because, of course, you needed a lot of electricity. In the 70s, all these transformers were also full of PCB oil. They're right next to the electrolysis plant in most of the time. So you get PCB contamination. And asbestos was the super hot thing in the 1960s and 70s. So yeah, they're full of them. So when we're looking at these sites, from our experience, where do you find the mercury? Well, the easiest place to look at it is underneath the electrolysis plant. This is an example from Bosnia. It's an abandoned site, and underneath you can actually see the drops of mercury everywhere on the ground. The wastewater network is another prime suspect. The brine regeneration facilities, which are often very close to the electrolysis site, and the disposal of sludges. I've seen sites in India where, you know, when they've cleaned their cells, you know, they just dispose their sludges everywhere in the surroundings, and they can have concentrations up to 500, maybe even much higher in mercury. HCH, I mean, yeah, it's quite clear. You find them in dumps of waste. We have, of course, in Macedonia, we see them on the site itself, but often they're dumped in the wider surroundings. In France, I think they're 10, 20 kilometers away from the site. As soon as there was a pit, they'll just dump it in. We also see HCH. The presentation is gone. So we see HCH also in areas really where the handling took place. So they would store it on the top surface. It would blow away by wind. It would really be in the surroundings. And last but not least, what I mentioned before, dioxins, you really have to look at the spent graphite alloys. We can usually find the dump sites. So this is a short overview picture of, you know, if we look at an electrolysis plant, you know, what are we looking at for concentrations? And I'll just highlight a couple. I have to time manage myself. So essentially what we would see that the floors would contain anywhere up to 80,000 milligrams per kilogram of mercury, and that's in the concrete. And what we see in the walls is concentrations up to 5,000, maybe you found even more. And the higher you go up in the building, the higher your concentration actually is. Why? Because it just evaporates and it somehow goes into the concrete. Now, it's a great fun if the roofs are then made of asbestos, then you have the asbestos that basically absorbs the mercury. What we also see in the groundwater, especially underneath these buildings, we find HCH if there has been production, but mostly underneath the electrolysis plant, we'll find mercury concentrations up to 1100. I mean, this is just some of the concentrations that we have found in the past. Brine sludges are often, let me see if there's a pointer. So brine sludges, you can find them all around in small dump sites, sometimes bigger. They look like basically gray material, a bit sandy sometimes. They can have really high mercury concentrations. It really depended on how good they were able to control their process and, you know, what the quality of their actual brine was that they used initially. I also see that, especially if you remove the building, you'll find the pure mercury around the foundations, but you'll find it around the sewer systems and a lot of other locations. Last but not least, and those are almost the easiest to find, is the huge dumps of HCH waste, mostly the inactive isomers that have been dumped. And they thought, oh, well, we've got this dump of HCH waste, let's just add the mercury waste to it, let's just add the asbestos to it. So they tend to be not very homogeneous, not always homogeneous waste dumps. So when you remediate a site like that, I think my advice at first is that no plant survives first contact with the enemy. I think it's a term from the army, basically meaning that if you open up a dump or if you remove a building like that, you can have planned until the end of times. As soon as you actually open it up, you'll tend to find different things. You'll have to expect the unexpected. you'll find things that start to complicate your disposal. You'll find mixed HCH and mercury contaminated waste where sludges have been dumped. You'll find mixed mercury and asbestos. So you have a building, the asbestos was in there, the mercury is in there, it will go into the asbestos. Okay, where are you going to get rid of that? You'll find mixed HCH and asbestos, where we've seen sites in Turkey where the asbestos roofs were basically collapsed into your HCH waste, and it was all, made into a nice pile. And last but not least, of course, you've got dioxins and mercury in the graphite anodes. Well, these are some of the pictures of sites that you'll see. It's very difficult to distinguish between this material, which is high in mercury content, this material, I think it's an ash actually, and sometimes you have the brown paste, which is HCH. So it's difficult to see visually what's there. So what we say is that when we do a remediation, we have to build variability in the execution. It's important to find a good balance between minimizing the mixing of the different soils and wastes and what is practically feasible. I know the disposal costs and treatment costs are very high for these sort of materials, but it doesn't make sense to do every square meter at some point because you'll be testing until the end of time. So you need to find a balance between how much you test and how much you can accept as like a mixture. And of course, the higher your disposal costs are, the more you will test and the more you will have to excavate separately. Of course, if we make a strategy for testing and it's really, really complicated, it's going to be very hard to execute in the field. So you'll have to accept that, there will be some mixing at some point. It needs to be a straightforward method. Everybody should be able to understand it. And there should be a flexibility to deal with surprises during the excavation. You might find barrels, you might find waste that you didn't expect. There's all sorts of things you'll encounter. I have to see. So basically, what we have done at a location in the Balkans is that we made a determination for our supervisors in consultation with the contractor that say, okay, we're going to excavate this site. At some point, we have to make a decision. This is soil, this is waste. It's very difficult to see, especially with HCH. Sometimes the soil looks like waste and vice versa. If it's waste, is there a removal possible? Can we separate the waste from the soil, or do we really need to make sure we cannot? If there's a little piece of HCH in 1 square meter of soil, at one point, are you going to say to the contractor, okay, just take this little, piece of HCH out of there, which will lead to actually different disposal method for the cubic meter because your concentrations will be immediately sky high. So you have to find this balance between what's waste, what's soil, and when do you still get it out, and when do you accept that this is a problem and we have to deal with it as a waste for the future. So if it's a soil, we have 2 types. It's more than 5 square meters, less than 5 square meters. We use an XRF. We basically develop a sampling protocol based on the XRF to separate layer by layer where it goes. I've got 2 more slides. So this is how it looks like from the top. You got your waste. You basically make squared areas. You check all the areas with visually the same materials, and based on that, you make your excavation strategy for your waste material. From the top, that would look something like that. So you would have a clean soil in this case. You've got mercury waste. You've got soil with granules. You've got compacted soil with HCH. You don't want to mix these two because HCH and mercury, they don't, the incinerators might not be able to accept that if your mercury concentrations get too high. So when you dig out, and I go back, you make sure that you dig out based on your XRF, based on your protocols that you have developed and that you have to agree upon with the contractor. And then in the end, what we have done at this site in the Balkans, we basically made a matrix and say, okay, listen, you got soil or you got waste, your chlorine concentration based on your XRF, because we cannot test the whole time, is, let's say, less than 100. We'll accept it that it's clean soil for mercury, for HCH. If your metal concentrations are below certain levels, we say, okay, this one's clean, we'll put it in that depot. If your metal concentrations are higher, it goes to a different depot, etc., etc. So we actually develop a number of depots where we put the soil in, and then based on that, we can do the real testing afterwards, and we try and avoid as much as possible getting a cross-contamination between the different types. So that was my presentation. I'm 2 minutes behind schedule, my apologies. Any questions?
But as we all know, and we have experienced that together, that calibration of the XRF for the different batches of waste and soil is very important. And that has to be done upfront, but has to be constantly...
Well, yeah, I mean, unfortunately, the XRF is not a holy grail, especially some of the better XRF, they all have a threshold limit between 4 and 8 ppm for mercury, which is already for some of the treatment facilities a problem. Also for chlorine, you cannot really go very low, and you'll have, of course, natural chlorine available. So and that's also what you say. You try to do, based on the information you have, your best estimate, your best judgment, and you try to limit based on that information as much as possible you can do. In the end, you still need to test it. But then you will test the depots that are outside, because it's absolutely impossible to test it with laboratory testing on site, because you lose just too much time.
What do you do about these hotspots when you find this high concentration mercury in the soil? How do you remediate them?
Well, in this project, the budgets were only available for the chlorinated hydrocarbons. So at that stage, the mercury contaminated material has been put aside until there has been a solution provided. So there's people around that probably can then give you some more information on that.
Good afternoon, everybody. My name is Xavier Ibarz. I work for ECON Industries as a business development and a specials project manager. And for more than 10 years, I've been working internationally in the hazardous waste industry, especially in the mercury waste treatment. And over the next minutes, I will explain the technology developed by ECON Industries to treat mercury and HCH compounds from waste from the Chlor Alkali plants, and afterwards how to transform the elemental mercury to mercury sulfide for its safe final disposal. So when we look at the agenda, I will start with a short introduction about the current situation. I will give some words about ECON Industries and what drives us in our daily business. Afterwards, I will introduce the available technologies to treat the contaminated waste on site and to stabilize the mercury. Then I will explain the VACUDRY technology in more detail, including some real cases of remediation projects. Afterwards, I will continue with the mobile mercury conversion unit to stabilize the mercury to mercury sulfide, and then I will finish with some conclusions. So when we look at the current situation, the demand of remediation of obsolete Chlor Alkali plants that were using mercury in the manufacturing process has increased considerably. Then during these remediation works, large quantities of contaminated waste, contaminated with mercury and HCH compounds, need to be treated. Due to the hazardous nature of these wastes, it is necessary to treat them using the best available treatment technologies for remediation and subsequent use of the decontaminated land, discarding landfill as an option. For the reason Taking into account all the previous points, ECON Industries has developed the most cleanest and efficient solution to recover sources from hazardous industrial waste based on more than 20 years experience and more than 30 industrial waste recycling plants. What drives us in our daily business is making clean, recyclable materials available for reuse to supersede in long-term landfilling and incineration, to reduce CO2 emissions, and to avoid waste export and large waste transports. Who we are? Well, ECON Industries is a family-owned business and was founded in 2003 as a machinery supplier, and we are based in Germany. Over the years, we have delivered more than 30 hazardous waste treatment projects, which 18 are VACUDRY units. And we are very involved in international working groups such as UNEP, UNIDO, or the Minamata Convention. So when we talk about on-site treatment technologies for mercury contaminated wastes, ECON offers a complete solution from extracting the mercury from the soil to the stabilization of the recovered mercury to mercury sulfide. The first treatment is the VACUDRY technology, and is to extract the mercury from the original waste. This is a low temperature vacuum distillation process, which is mainly used for contaminated soils or sludges. Once the mercury has been extracted from the soil, this must be disposed in a safest manner according to the authorities' regulations. This can be done using the mobile mercury conversion unit, transforming the mercury, well, the elemental mercury, to mercury sulfide or cinnabar. The concept of the VACUDRY technology is to separate substances with a boiling point up to 450 degrees, or to decompose substances and evaporate the volatile parts. Specifically for mercury and HCH compounds, the input material is fed into the VACUDRY, where it will be thermally treated, obtaining a clean or mercury-free solid material at the end of the process. The mercury is recovered in the condensation unit, and the off-gas passes through the off-gas cleaning system to extract the volatile organic compounds and other persistent pollutants in case that we have them in the input material. Well, VACUDRY technology is a physical separation by vacuum distillation with the highest quality of recovered resources due to the vacuum and low temperature treatment. Here we can see that from contaminated soils and sludges with mercury and other compounds, we recover resources like clean soils, water, oil, or mercury using the VACUDRY technology. Here we can see the VACUDRY flow chart where we can differentiate the different parts of the plant. Starting with the feeding unit, the material is fed into the batch-wise evaporator using a tube chain conveyor or belt conveyor, depending on the input material consistency. Once the feeding is complete, then we can start with the batch treatment. As you can see here, there is a thermal oil system around the batch evaporator heating the material indirectly. That means that there is no combustion inside the chamber. Also, the shaft inside the chamber is heated to increase the heat transfer and heat the soil properly. At the top of the evaporator, we have the vapor filter with the aim of catching the dust and preventing it from going to the condensation unit. Then, during the VACUDRY process, the pressure is set until 50 millibar absolute, that's a high vacuum. And as the material temperature rises, the water, the oil, the hydrocarbons, or the mercury starts to evaporate. For example, the first evaporation phase is going to be the water. As soon as we are reaching the boiling point of the water in vapor form will go through the vacuum filter, through the vapor filter, through the condensation unit, and we are going to recover the water in the condensation tank. As well, it's going to happen with the mercury and with the other components. As soon as we are reaching the boiling points, the mercury is going just to condensate into this condensation tank. The remaining off-gas stream, including the non-condensable components, is then passed through the vacuum pump. Then it will pass through a thermal oxidizer where the persistent compounds are going to be heated to 1200 degrees Celsius during 2 seconds to destroy them completely. Afterwards, it's going to go through a cooling system and separation system as well, and activated carbon before it will go through the flue stack. And once the batch is complete, then we discharge the clean solids from the bottom, and then we can start feeding and we can start treating the next batch. Then in the next 2 slides, I will present 2 real cases where the VACUDRY technology has been used to decontaminate on-site soils contaminated with mercury and other hazardous substances. The first one is an on-site remediation project in France, where 70,000 tons of mercury and PAH contaminated soil and building rubble had to be cleaned in an industrial facility. For the realization of this remediation work, an ECON Industries VACUDRY 12,000 was installed. And after the treatment, the mercury-free soils could be reused on-site as a building material. To achieve the target from 1 ppm mercury in the input material, the material is heated up until 350 degrees, and we set a pressure of 50 millibar absolute to treat and to extract the mercury from the waste. Then, once the mercury has been extracted, then we recover as well the water, the mercury, and we clean the soils. Here you can see the input material with a 50 ppm mercury concentration, the recovered mercury on the condensation unit, and the output material with less than 1 ppm. Then the second real case is an on-site contaminated area in India, where in order to treat mercury contaminated soil from a thermometer factory, it was necessary to implement a technology that would allow for on-site treatment rather than transporting contaminated material over long distances. In this case, we built a semi-mobile 3000 unit. It's a smaller unit compared in the previous case. And what we follow is the same procedure as before. Once the material was fit into the chamber, into the evaporator, we heat the material until 350 degrees. We set a pressure of 50 millibar absolute, and then we start extracting the mercury from the soil. Here you can see as well that the material input was 80 ppm of mercury. The initial concentration of mercury is not really important. We can have more concentration. It's just going to take a bit longer, the treatment batch time. Then the condensate, mercury, and the output material clean and free of mercury. Well, regarding the mercury stabilization, once we extracted the mercury from the soils, it has to be stabilized. Then ECON has developed an on-site mercury conversion unit to convert elemental mercury to mercury sulfide. The unit operates according to the formation reaction of the mercury sulfide, mixing mercury, elemental mercury, and sulfur in a stoichiometric ratio to form mercury sulfide. The mercury sulfide is a non-toxic material and is the most stable and insoluble mercury compound. Then the mobile mercury conversion unit makes sure that there is only one single on-site process step which is protected from any type of leakages. The whole conversion process is very safe, as we are working in a liquid phase reaction and as well under inert atmosphere. Here are some references about the mercury stabilization. using this unit, we have stabilized more than 500 tons of mercury. To be more specific, 400 tons of mercury were converted in the UK in a chloralkaline plant, and another further 130 tons were converted to mercury sulfide in a chloralkali plant in Poland. And then I finish with the conclusions. Based on the detailed information that I gave you previously, then we can say that ECON technology is a proven on-site treatment technology, from the treatment of the mercury waste to stabilization of the recovered mercury for its safe final disposal. Then we can say that treating the waste on-site reduces significantly logistic cost and avoids unpredicted transport risks during the waste mobilization from site to site. Then is a high flexible system that allows treatment of different kinds of waste. In the same unit, we can fit solid material, liquid, or pasty. Then there is a high degree of decontamination, higher than 95% of solid waste, enabling it to be reused as a backfill material during the site remediation. And at the end, it's a very low carbon footprint technology due to the advanced technology and the use of renewable energy supply. And the system fully complies with the requirements laid down for the regulatory authorities. And we can say that it's a proven, profitable, reliable, and green energy power technology. Thank you very much. And if you have questions, feel free to ask me.
Small question, you mentioned logistic and transport cost. You didn't say anything on treatment cost. Can you give an indication on the treatment for mercury polluted soil?
Well, for example, if we compare other thermal desorption units from the past, we can say as we are working under vacuum and we are reducing a lot the boiling point of different substances, we are requiring less power consumption to extract the mercury from the waste. I can send you some numbers if you want. Just give me your email address, and I will send you some specs about power consumption and other consumables like nitrogen for the inert atmosphere or something like that.
So sorry for I have to be seated and I have to be wearing glasses, but I am confident I will be able to still explain what I want to explain today. Good news is that I have, as Guido said, 2 presentations. First one is to speak about treatment of mercury and mercury wastes. And the second one is more oriented to case studies. Due to the fact that I had to deliver the material separated, the presentations are separated. But the good news is that I will be not using the full time that is allocated because some part is repeated in both presentations. So my name is Castellnou. I'm working currently at BATREC Industry. It's a Swiss company. I've been dealing with hazardous waste for more than 25 years and moving waste, trying to find appropriated waste treatment for hazardous and difficult waste has been my main goal. Now I'm involved with BATREC. So, vale. BATREC, as I told you, is a Swiss company. We are in the middle of the Alps, in a beautiful landscape where you don't imagine that you can still find some mercury treatment. And so we are part of SARP Industries and within the Veolia group. We have 5 core activities. We deal with mercury stabilization, we deal with mercury containing waste treatment, oil and gas absorbents recycling, activated carbon, and battery recycling. Of course, here we will concentrate on what's related to mercury. Vale. So I'm not gonna insist on what's related with Minamata Convention because it has been already treated widely in the other presentations. The thing is that still mercury is present in many industries, including oil and gas and non-ferrous metal industry. And the parties that have ratified Minamata Convention have are committed to taking action to limit mercury from the use in both everyday products and industries. And that's what BATREC is trying to be doing. Yeah. So for stabilization, so what stabilization means, other colleagues have described what we do, and here we have a patented process for that. We do is we have metallic mercury, and then we have a stabilization reagent, and what we have is cinnabar. Next slide. Thank you very much, Guido, because I have to remind to move both. So, okay. Then here the mercury sulfide is then a non-toxic and most stable mercury compound, and the most insoluble mercury compound. Here, okay. It's not centered, but we still see that. So this is a scheme of this process. What we do is we're dosing the mercury, and with the polysulfite solution, then we precipitate the mercury sulfite, then we filtrate the mercury sulfite, and we are doing the regeneration of the polysulfite solution. Then what we have as numbers, I think I skipped something, sorry. Difficult for me to see. Yeah, so I wanted that one. Yeah. Vale. So a mass balance that we can show is that with 1 kilo of mercury, we turn into 1.19 to 1.25 kilo of mercury sulfite. We have here a picture of this cinnabar, and we have, if you are interested, of course, this material can be shared. We have the composition of the mercury sulfite, this fine grain size, and this is a filter cake with a low humidity. Afterwards, and that's covering one of the questions you asked, the audience asked before, what we do with this mercury sulfite, according to the regulation that's guiding us, is send it to a salt mine in Germany. This salt mine disposal consists of filling an excavated salt mine with hazardous waste. Our waste is not, I mean, we said it's cinnabar. It could be considered as non-hazardous waste, but it was decided that it could be disposed this way. Then the deposits are in underground to depths from 500 to 800 meters underground, and there's no further solidification required because it's already soiled, and there's no requirements regarding leachate. So we spoke about mercury stabilization. We are speaking about liquid mercury. That's what we do with the liquid mercury. But of course, the mercury appears to be in other forms, in other presentations. So we can find it in sludges, in slurries, in mercury absorbents, when we decommission waste in contaminated clothes, PPEs, and in absorbents like ceramic bowls. Here, what we wanted to show it was some pictures of all this mess we received, some old labs that they're sending some waste to us. So it's some idea of what we can receive from different perspectives. So what comes to tell that in addition to this stabilization, we have at BATREC other treatment technologies. to be able to take care of these other mercury contaminated waste, which is not liquid mercury. So we have a distillation unit for mercury waste. Then we have here, you can have lamps, you can have thermometers, you can have button batteries. What we have to do is first a distillation, first sorting out, which is quite manual, as you can imagine. Then after this sorting out, we have to go through the distillation process, and then we recover the mercury, and the mercury will follow the stabilization on our stabilization unit. So some technical details, but I'm not going through very deep. Anything you would need further, I can provide. But by heating to over 360 degrees, the mercury contained in the waste vaporizes and condenses again as pure mercury in a condensation column. Then we also, as we saw in that scheme that show other types of mercury contaminated waste, we also need to be able to desorb the mercury when it comes to a solid, when it comes to activated carbon or contaminated soil or absorbents. Then we need also to be able to recover these materials to reintegrate the industrial processes. That's when we have our thermal treatment step. And here we receive soils and sludges that are contaminated with mercury, or we can also take personal protection equipment that we find in the commissioning or any kind of project. They need also to get rid of that kind of waste. So this is the idea to show you. So until now we've seen the stabilization for liquid mercury, the distillation unit, and now we see a thermal treatment step for the idea to cover all the possible presentations of mercury contaminated wastes. Again, this is a kind of a recap. So we, no, not here, but here. Yes, so metallic form, what we call mixed mercury waste, that we make the distillation, the mercury absorbents that we can find in oil and gas industry, and also here I would be talking about deactivated carbon, and then liquids that can be containing mercury can also be integrated in our processes. So that's for the first presentation. Okay, and then we can go to the next one. So I'm happy to say for the audience that we can save some slides. So again, what BATREC does and what BATREC means and we are part of this group, etc., can be skipped. Minamata again can be skipped, and then we will go to this slide where we're talking about what we will show you, a couple of case studies. Chlor Alkali industry and gold mines will be the chosen ones. And what we're proud to talk about is that we have accomplished projects in the Chlor Alkali industry and the gold mines. Decommissioning of mercury-based Chlor Alkali plants. We have dealt with quite a lot of stocks, remaining stocks in Europe. And we have treated more than 1,800 tons as of 2016 from Spain, from Belgium, from France, from Italy, from Hungary, from Slovakia, Czech Republic, and Switzerland. And the second case study that will be presented here is industrial gold mines. They are still continuing production. They continue production worldwide. And we are happy to say that we have treated more than 500 tons as of 2016 coming from the LATAM region. Okay, so that's then okay. We have other, of course, other clients, but it's not the chosen one here. I will not show today a case study from oil and gas industry. Again, we can skip that because it's to frame the. Here we will speak about pure liquid mercury. So that was to frame the treatment technology. And then I think we can go to this slide. In order to do what I'm going to describe, we all know that we have to have traceability, and this is the key. And we are moving hazardous waste. It has to be under Basel Convention, and it has to be done in a certain way. So what we try to do is a turnkey solution, a key turn, I don't know, turnkey, thank you, is a turnkey solution. And what we do is to provide the customer, as from the start of their problem, we try to give some advice for labeling, some advice for packing, we can bring people on the site, then we will have to transport that to BATREC, and then we will have to treat it. And after treatment, we will have to provide some reporting, and not only about what we do, but also about what is done afterwards, which is being transported to the salt mine. And that's what this slide means. So the two case studies that are provided with a detailed examination are, so what we see, what we will go through is the TFS formalities, what it means going through Basel Convention for export of waste. Then we will show some local operations, what supervision of packing, labeling, shipping into maritime containers, and health and security protocols, whatever is needed at customer site. Then we take care of the road and maritime transport according to ADR and IMDG regulations, and the process that you already know, and again, the full traceability chain that I showed in the previous slides. So here we have, I think pictures speak very, very well of what we about what we do. So we have some safe storage. That's a case study of a Chlor Alkali plant in Spain. We will be seeing some Spanish mercury. We've heard before that Spain had quite a deal part of mercury in Europe. So we've been dealing with that. I'm very proud to be located in Spain and taking interest on this part, and also in the Latin America market that we will be seeing afterwards. So that's as an example of storage, of a safe storage of mercury in a Chlor Alkali plant before shipment. There's another example of a safe storage facility before shipment. And that's an example of what's the transport of mercury from the producer to BATREC. This is something that we also are there to provide advice for how to transport, for how to label, for how to make it happen in a safe and sound environmental manner. That's another example of transport, some pictures again. And then the second case study that I will show you, that I will be going more into detail, but because I find that is more important to show what can be done when it's far away. Yeah? The example, okay, you can think Spain, okay, trucking to BATREC, okay, we know how to do. Now what I will show is this other case study from a mining industry, where we provide again door-to-door services, and we make this on-site supervision, and we pack, we label, we load, following Basel Convention, and we've done that for more than 500 tons in more than, I would say, 10 different projects. So, vale, aquí estamos. So here we are the part of the supervision works at the mine, and we are staffing the maritime containers. That's a guy from us. That's a guy from Veolia, of the country where we were shipping. So we supervise, we inspect the mercury containers, we label, we staff the maritime containers, and we apply Basel Convention in every kind of things we're dealing with. So here you have an example of the health, so of the PPA material and the labels. And here we have another view of the supervision works. So at the mine, we supervise how the guys have been, even if we have to be checking if it's in good shape, if the mercury containers can travel or not the way they are. We can refuse if one container we don't want to ship it. So, and until the stuffing of the maritime container, and of course according the paperwork. Here we have, so we go ahead all the works. So here we have the road transport, local, so we take care of that. There's a big issue when you travel with mercury in all these countries. You have a lot of people following you up. You have the local police, you have the journalists, you have a lot of people interested for good and bad. And then, so you have a local customs processes as well. And then the custody at the port sometimes is requested. So we support that. We coordinate also with International Freight Forwarder, this part. And that's when we go up to the port. So our guy is going from mine to port. And so we do the maritime transport from the port of loading at the country of origin to the port of discharge in Europe, and then first vessel, and then trucking into BATREC. And so then we do the customs at the arrival, then the trucks, the unloading at BATREC, the trimming in our stabilization plant, and the shipment of the mercury sulfide to salt mine. All these steps are included, and proof has to be shown to the customers to show this traceability that I spoke before about. And I think that's everything I wanted to tell you, and to thank you very much for your attention, and to invite you all to Switzerland. It's a small plant, but if you organize ourselves, we can still make it. Thank you very much.
Thank you, Angels.
My name is Boudewijn Fokke, and I've been working for quite some time together with Guido in the company Tau. And since 1 year, I'm retired and work still for Tau, but then as an independent consultant. This project is about a Tau Foundation project. It's financed by the Tau Foundation. And it is in the scope of the corporate social responsibility of Tau. And we're not doing it on our own, but lucky to hear that IPEN was also presenting, because we do that together with a partner of IPEN, which is Nexus 3 Foundations, the former Bali Focus company in Indonesia. And then we do that with the Mataram University in Lombok, and together with a mining company called Aman Minerals in Sumbawa. So we have covered 2 islands, Sumbawa and Lombok. And this project is about the artisanal small-scale gold mining using mercury on Lombok and Sumbawa. So I will first share the project objectives. Then the project is, of course, divided in phases. I will go into the phases. But before I go into more details on the different phases, I would just want to share 2 slides on the common practice which we encountered in the villages we visited on the Sumbawa and Lombok. Of course, we want to raise awareness on the impact of artisanal small-scale gold mining using mercury. But this is a very important aspect of our project. As long as the tap is not closed, we do not implement any remediation, of course. So the tap should be closed. Mercury should not be used anymore on site. And that's why a very important aspect of our project is the awareness raising in the villages. And that is mainly the task of our IPEN partner, Bali Focus, now Nexus 3. Then, with our project, we develop a remedial approach. This remedial approach will be pilot on a selected site. And finally, with all we have discovered during this pilot, with all the loopholes and traps, we will then develop a toolkit to remediate mercury contaminated sites where the ASGM has been stopped. Okay, the project phases. The first phase is the inception phase, and in the inception phase, including an investigation and the selection of a pilot site. The pilot site should represent the way it is done in this island, and it should have aborted the use of mercury and stop all activities. So that was the first phase, and that is completed. Then a tier 3 risk assessment to give support for the remediation. That's also completed. And now we are starting with phase number 3, which is the preparation of the remediation and the monitoring. And of course, the outreach is already through the whole project done. Okay, I told you I would give some details on the process of artisanal small-scale gold mining at these villages, and I think they are more or less representing the practice in these 2 islands. I've been in Suriname also on artisanal small-scale gold mining sites, and there the practice is different. But we visited 11 villages in Lombok and Sumbawa. And the majority of the families in these villages were all practicing artisanal small-scale gold mining. It was difficult to find a compound, a family compound, where they were not doing this. There were, I would say, 80 to 90% of the population in these 11 villages, and there were more villages where they were practicing artisanal small-scale gold mining using mercury. And this gives an enormous amount of mercury emission to the surrounding, and I will show you that later. But the people are aware of the negative impact. I mean, they get children. I did not choose to present, but we have terrible pictures of children without hands, children without ears, the eyes are missing, and all kind of other effects. It's really horrible to see. That's why I don't present it. So they do not use anymore groundwater from the domestic wells to drink. They all buy bottled water, but they still use their water for all kind of other things, like watering trees, watering the cattle, washing, and so on and so on. But we have also seen that because they are aware, some families only use mercury for high prospect tailings or ore, sorry, and low prospect batches are brought to the cyanidation plants. And very few families have stopped. Now, what is the process? The process is the mining somewhere in the hills or the mountains outside the villages. They transport the bags in these rice sacks, which around 20-30 kilograms to their village. Then they grind it or crush the ore. They mix it with water and mercury. They put it in a rod mill. There's not a ball mill, but a rod mill. I have some pictures later. Then they drain the tailings from this rod mill into small basins and using gravity to separate the excess of mercury and the almangan. And then finally they have the almangan and they burn that and then they sell it. They sell it to the gold shop, and the gold shop is also the shop which trade illegally the mercury, because mercury is traded illegally in these countries, or on these villages. Here are the pictures. This was during our survey. Here you see the ball mill. In this case, there were 2 ball mills on a just simple constructed platform. It's brick laid with a concrete slab. Then there is a small pit collecting the coarse material, and then a larger pit, not lined, where they drain all the tailings, and then just by infiltration, the tailings get dry, and the tailings are always sold to the cyanidation plants, because with cyanide they get more gold out of it, so they sell that. But here, so this is the ball mill, has a lid, it's milled for 5 hours. Then here you have the sediment and the mercury, including the almangan. Now, it's a timely process, but finally here is the last stage. He's pouring the mercury with the almangan in the cloth. Here he's pressing with his hand the free mercury out of that, let's say, mercury and almangan. And finally, in the cloth, he has his almangan noodle. And this is 20 kilograms ore, gives you this amount of almangan. Now, finally, it's ready for burning. And here, I call it sophisticated amalgamation burning station. It's just inside their compounds. And family are standing around and looking in, because it's nice. You see first silver and then you see gold. So I think that's the largest exposure route. It's inhalation of the direct burning, or it's heating or evaporation, we call, of the almangan in these stations. And you see it everywhere. But more and more gold shops also facilitating the burning. But these shops are inside the villages. They are inside small towns. So it doesn't help, actually. Now, what I did here is a generic initial conceptual site model of a village where you have this process ongoing. All family compounds have their ball mill, their basin, sedimentation pond, and their wells, because near all these ball mills is a well, because they need a lot of water. So domestic wells are being dug, all especially for water to be used in this process. So what happens, due to all this handling of mercury on site, it evaporates by the burning, but also by the deposition of mercury spills around. And this evaporation settles, it settles again, it deposits on the leaves of the trees, on the fruits, on the grass, the cattle is grazing, and so on and so on. So it's everywhere spread around. My colleague Daniel Lutz said this ecosystem is inhaling, respirating mercury, because they burn it, it's deposited, it gets hot during daytime, evaporates again, gets cooled, and settled again. So it's everywhere. What we did, and what that proves, is that I took some baseline samples far uphill, away from the village, and there mercury was detected. Then the water. Here, all these infiltration of sediment ponds, they infiltrate their water into the groundwater. And these these wells are very nearby. So the groundwater is also impacted. Now here actually is a short list. The sources, of course, the use of mercury in the amalgamation project, the groundwater in the wells, but they are below the drinking water norms, but just above the intervention values, but it contains mercury. And it's not only the well water, but it's also the sludge in the wells. The topsoil around the rod mill location is contaminated slightly. The subsoil and the sludge in the ponds, they vary from slightly to moderately strongly, and it depends on the time we took the samples. Samples taken just a day or two after they have been operating this were very high. If we did it a bit later, it was lower. So that proves also that it is that it's evaporating, depositing, and so on. There's a constant process. And then high concentration are measured in the pond, where the highest levels were measured in the ponds where they were recently used. the topsoil in the villages is slightly contaminated. And the conclusion is that the primary source of mercury contamination is the use of mercury itself, and then the secondary source is the sedimentation pond and the topsoils, and then the diffuse contamination in these villages. Now, what are the pathways? Spills during amalgamation, evaporation during burning, infiltration in the topsoil, infiltration in the groundwater, the use of contaminated groundwater in the households, irrigation of kitchen gardens and watering livestock, runoff, of course, and finally it ends up into the river and into the ocean. Now, the receptors are the villagers, of course. I will not repeat, but inhaling and on the consumption. These villagers are subsistence farmers, so they use, here comes it again, a single food basket. So they grow their food and they have their livestock on the same land which is contaminated. So they inhale, they eat, and they wash. And it's all slightly contaminated, but at the end, it accumulates in the body and you get these horrible effects. And of course, the same counts for the ecosystem. We did not do any survey on the sediments, but there are enough studies that proves that the sediments in the river are contaminated with mercury. Now, based on the phase 1 activities, we selected one site to have a remediation, and that is a site where, and it was hard to find, a family stopped with the use of mercury. They actually stopped the whole process of artisanal small-scale gold mining. But here in detail, what I showed on the larger picture, so the burning, infiltration in the first settlement pond, infiltration in the soil of the large sedimentation pond, and then of course the deposition of the mercury everywhere. Now this is, here you see the numbers. The numbers are standing for the gaps in this initial conceptual site model. Based on that, we made a sampling analysis plan, and the sampling analysis plan gives us the following results. And, yeah, I'm nearly finished. And unfortunately, the site is inundated, and now we have to do verification sampling. But no high concentrations, only high concentrations at the lower spots where the runoff was collected and at the sedimentation pond. Now, this is how it is. The sedimentation pond is filled, and this is the contamination itself. To justify the remediation, we did a tier 3 risk assessment, and of course, here you see what the result is. The most critical exposure routes are consumption of vegetables, consumption of meat and livestock products, groundwater exposure, indoor exposure, and soil exposure. And this justifies the pilot remediation. We are now on the phase of preparation, and what we what we think we want to do is to dig out the contaminated soil, mix it with biochar, and biochar will immobilize the mercury, and then put it in a depot and put vetiver grass on it to prevent erosion. And that's still under dispute, but the vetiver seems to absorb in the root system mercury. And based on the experience, we will make a toolkit for all the villages, or let's say the sites where the ASGM has stopped, and then they can use this toolkit to remediate their site. And it should be low profile, less cost, otherwise it will never happen, because this community, these communities, they don't have money for expensive solutions. This is it. Thank you for your attention.
Thank you very much. What happens with the cloth?
It's a precious thing for them. So the cloth is just used for in all batches, and it's like, yeah, it's a very strong cloth. It's like I don't know the English word, zeemleer.
Yeah, it's like
it's an artificial leather, and it's very strong because
so they keep reusing it.
Yeah, they use a lot of force. Yeah. There's still questions on our approach, how we safely can crush the platform and other things. But this session gives me already some input on other techniques.
Well, great example for grassroots cleaning of these villages.
Yeah.
Next presentation is from Conde. It's the remediation of mercury contaminated site, the case of the Almaden dump and the antique mercury metallurgy facilities of the Almadenejos.
Good afternoon. My name is Isabel Conde. I work as a manager of the Mercury Technological Center. I'm going to talk about the practical cases in the remediation of mercury contaminated sites. I would like to say that I've been working on mercury for 25 years. First, I worked on the production, management, and handling, and over the last 10 years, I've worked on remediation projects trying to solve the environmental problems caused by mercury. I'm going to jump over this one because we've already spoken about the mercury, uses, problems, etc. But I would like to give you information about the first global producer of mercury. The oldest mine is in Almaden in Spain, and they say that a third of the mercury consumed by humankind comes from here. They've always been managed by the state, first by the crown. In the last few years, it was a public state called Mayasa, which is part of the Treasury Department. In the year 2000, the company, aware of this environmental situation caused by mercury and because of several technical problems and economical problems, decided to put a hold on all the activities related to mercury. In 2001, the activity gradually slowed, the actual mining of the mercury. Okay, in the year 2003, it was halted, the primary mercury mining. The trading of mercury continued until 2011, when the European regulation on mercury prohibited it being exported. Given this situation, the company looked into different actions. We have to bear in mind that these mines of Almaden, as it's been called, has been exploiting mercury for over 2,000 years, and that means that there is a large historical and cultural heritage that the company decided to set forth. Currently, this historical and cultural heritage is the Almaden Mining Park, is public, it can be visited, is part of the World Heritage since 2012. In parallel to the restoration of the historical and cultural heritage, we also did an environmental restoration. So in 2011, after the closing of all activities with mercury, they decided to create, together with the Environmental Ministry, an environmental research center. Taking the place of the management company. So they tried to give a technical and scientific solution to the problems of mercury mining. This is the first case of remediation of mercury contaminated areas, and the most important carried out by the company. Just to give you an idea of the size of the problem, this is a picture of the year 2005 after the halting of all mining activities. This is the dump, where this small building is where I'm currently working. This is dump that had byproducts from the mining industry. It has a 3.5 million waste amount, occupied area of 9.1 hectares, a top area 4.9, and with an important slope, 4.2 hectares. And the environmental impacts are what we were saying before: the atmospheric contamination, environmental contamination, the contamination of the waters around the area, the change of the morphology and landscape, and geotechnical risks. When we studied the best solution for this environmental problem, we did a classification of the dump and of the groundwater. This started in 2003. These are only just some of the examples. We took samples for a year, for instance, of the surface water going through the dump, but also through the further areas. We're talking about areas or points 15 to 20 kilometers far from the mining location, and we did a campaign of surveys. There was surveys within the dump, but also around it. And there we saw initially their composition, and also we looked at the taxology of those samples. With the classification of that surface water, we reached the conclusion that the dump had elements of with a high level of mercury, but the area where it was on, it had very low permeability. That means that with regard to the surface water, it didn't affect it so much. However, it did affect the environment and therefore surface water around it, because there was a lot of lixiviation or leachate. We presented two alternatives. One was to transform or transport the mercury to a new safety dump, which was not viable due to the high environmental and economic impact that it would mean to move all these materials. After the classification of all this work, we decided to do an on-site treatment of the dump through the encapsulation of the dump. It's done in different phases. The first one was the new dump forming. Do you remember that I said that this dump had slopes of up to 60 degrees? So it wasn't feasible to be able to put the synthetic materials needed to isolate it. So we moved over 500,000 cubic meters of material. Then we did the dump sealing with the insulated material. And here you can find some images of the sealing of that dump. And how did we do it? First, we put a bentonite layer so that there is no puncture of the plastic, so that they cannot break. Then we put a barrier at the top so that the water doesn't rest on the waste. And then this is the insulating material used that you can see here in the pictures. I'm really sorry, she's not speaking very clearly to the microphone. Then we also put a support for the waters, and then we also put a reinforcement material, and then we placed all of this and revegetated all the area. This is an example of the slopes with a lower inclination. And the only thing that we did was to, in the last layer, we put some meshes called geocells, which created more surface contact between the soil and the material covering it, or the filling material. The third phase was the installation of a collection, circulation, and evacuation water system, so that we were able to avoid the erosive effects of the water. We didn't want puddles being created that could erode the material and reach the waste. And then, I'm missing one slide. Well, there's a fourth phase, which is the revegetation of the dump with grass and other materials. All the classification work before the restoration took place, both in soil but also on the dump, as well as all the monitoring of the waters and all the surveys carried out for groundwater and surface water, are loaded on this database, which is open, public access. If you go into this link, you'll be able to see the evolution of the surface and ground waters since 2005 till now. You can also see the levels of mercury in the area around the dump. Here you can see the efficacy of the restoration work. This is from 2005, when we were doing the remodeling of the slopes, And this one is from 2008. Once we had given a new shape to the landfill, and we were encapsulating it with the insulating material. As you can see, the mercury on the ambience, on the atmosphere, we could say is 3,000 times less. And here you can see the streams contaminated with mercury. These are the years in which we had the material movements. We reached values up to 10 ppbs in survey points that were about 15 kilometers away from the dump, and how those points have normalized, and currently we have values below 1 ppb. Despite that, this is work that is undergoing and that we continue monitoring, because this is something that happens not just in Almaden, it's not just an effect on Almaden, but there's also the constant problem of the mercury radioactivity. We can conclude that the restoration works managed to eliminate or reduce the evaporation of mercury in the area of Almaden. We also managed to reduce the emission of particles with mercury and reduce the lixiviation towards the nearby streams. I was saying before that the Technological Mercury Center is in charge of doing environmental monitoring works in terms of mercury. So here we have also remediation projects. For instance, I'm going to go now into the second practical case. 2 minutes? Okay. In this location, this is called the Cerco de Almadanejos. It's in a small town of about 100 inhabitants, close to Almaden, 12 kilometers southwest of Almaden. It's a metallurgical treatment plant, and we haven't done any classification of the location. The challenge of this, well, here we have 5 furnaces, old furnaces of cinnabar, and this area is considered to have cultural heritage. So no work can be done without an archaeologist and without the authorization of heritage, of the heritage department. There's no classification or characterization in itself, but there are some studies that show that the Cerco de Almadanejos is an area of atmospheric contamination by mercury. This is the average of contamination by mercury in the area of the furnaces. When we have to look at the different alternatives, we looked at the different possibilities, and we based ourselves on prior actions. In the year 2015-2016, we had a remediation plan in Mongolia, where there was a mercury discharge with a lot of contamination in water and in soil. And we used samples of the location, and we used different techniques. And then on site in Peru, we did 2 tests, one with a stabilizer, a chemical stabilizer, using a low oxidation oxide. And these studies and the characteristics of the new location made us do certain trials, and the results have been very positive, and we've managed to achieve contamination reductions of up to 90%. Given the characteristics of the location, this makes us think that the on-site solution is a possibility for the Cerco de Almadanejos. Our objectives are obviously to eliminate this contamination focus in the area and to be able to recover these old facilities, because who knows, in the future it can be used within the mining plant of Almaden. We're still working on this. In the next 2 weeks, we're going to assess the land again, and we're going to assess this technology as well as others. Thank you very much. This is ongoing work.
Maybe I missed it, but how many mining sites are there in that region?
Currently, there are no active mines at the moment. There used to be 3. The main one was the Almaden, where the dump that I mentioned was. Close to it, there was another mine, open mine, that's also stopped operation. And then there's another underground mine, and none of them are in production. None of them are in production though. One of the strategies for Mercury in the EU included the closing of all the primary activities on Mercury, including mining of Mercury. And that's why the 3 of them are no longer in operation.
Maybe one question on the landfill. So now you kept the landfill with plastic layers. On one hand, mercury is forever in the landfill, but the plastic has only a quite limited time. So when do you expect that you will have to renew?
Yes, when we did the characterization and we looked at the probabilistic analysis of this landfill, we're talking about a 2 millimeters thickness, high density plastic, and that gives us at least 50 years for the synthetic encapsulation. But we're also working in this area, and we do maintenance, annual maintenance of the landfill, cleaning the channels, making sure we see if there's any problem due to the sludge. Exactly. In fact, there was a land movement, and therefore we've had to replace the plastic since then. But we have also the environmental monitoring to check if there's something, if there's problems in the encapsulation, obviously.
Okay, thank you very much. This was the last presentation of today. We are more or less on schedule. Maybe
I did have a question for some of the technology providers, Minamata, ECON, and BATREC, who all seem to they have technologies for treating mercury, stabilizing mercury. And one of the comments that was made I thought was interesting on treating mercury reduces the logistics and transport costs involved before sending for final disposal. It seems like all the treatment is being done in Europe. I think it was BATREC described a project that they were working on importing mercury from a Latin American country, but it looked like they were importing liquid mercury, metallic elemental mercury. So there was no stabilization being done at that site in that country. And so I'm curious, is there any thinking on the technology provider side about possibly providing the stabilization technology to be installed in other countries, for example, in Latin America, where there is significant amounts of mercury that is still being produced as either byproduct from non-ferrous metals production, and being also seized from artisanal small-scale gold mining operations.
Ben, I think Econ Industries is very, very, very eager to answer your question.
Okay, thank you.
Hey Ben, this is Xavier from ECON. Yeah, well, we are supplying the machinery to stabilize the mercury on site. That means ECON is a machinery supplier. We don't operate the plants, or we don't offer the service to stabilize the mercury. We just sell the stabilization plant to the clients. And currently we have some negotiations with some companies in Latin America and as well in United States.
Okay, great. Thank you.
Yeah, Angels from BATREC speaking. So together what with Xavier has said, also the solution of BATREC for stabilization is a patented one. So meaning that this technology, where Xavier participated, life is very curious. So Xavier is the owner of the patent of the stabilization of, one of the owners of the patent of stabilization of BATREC. But what I mean is that this technology, of course, can be built in another part of the world. It's a question of willingness or politics or whatever of the company. So yes, both things are possible, together or separated. Thank you.
Mm-hmm.
Okay, thank you, Angels. Any other thoughts or comments, Ben?
That was the only question I had. I think I wrote down, I was on the agenda to do a conclusion, so maybe I can just launch into that if that sounds all right, Guido.
Yes, go ahead.
Okay, well, I just have some summary points from the session today. So thanks everybody for your participation and for sharing your expertise with us. So to begin with the session, we were showed a number of cases where mercury and POPs were concurrently released from Chlor Alkali facilities where possibly pesticides were also being produced. And so we learned that it's important to perform historical assessments of these production facilities to determine potential range of contamination. And we learned about mercury contamination as legacy of chlor-alkali production in the CE region. That sediment contamination leads to fish contamination, which is the main pathway for human exposure to mercury. So something that we really want to get a better understanding of and control over, and that there are studies showing the downstream impacts further away from facilities, so that these mercury impacts are kind of expanding beyond just the immediate region where the contaminated site may be. We also were shown an interesting graphic that I thought was pretty cool that shows mercury levels in oak bark surrounding a factory in the Czech Republic. So thanks for sharing that one. So even with remediation, mercury contamination persists a lot of times. And so sometimes it's about figuring out the level of remediation that is actually possible or desirable. And IPEN created a contaminated sites guidance that contributed to the Minamata contaminated sites guidance, which was adopted at COP3. And I apologize, I failed to mention that there is a mercury contaminated sites guidance that was recently adopted by the Minamata Convention that is available for use and download on the convention's website. Guido taught us that technical HCH it stinks, and and so it was only sprayed for potatoes for a short amount of time. Then only the active isomer was used, which created lots of waste. And so it's kind of interesting to learn about the history of some of this chemical use and where the waste comes from and why things are used. Mercury and HCH contamination can be found at chlor-alkali sites in roofs, floors, walls, brine sludge, groundwater, soil, foundations, and sewers. And more. So really, Guido made the point that when planning for site cleanup, expect the unexpected. As you progress, more will be revealed. Build in variability into the execution, which I thought was a really important point. We learned about mercury and HCH waste treatment from chlor-alkali plants from a number of providers, from ECON, BATREC, from IASA. Technology developed by ECON Industries to treat mercury and HCH contaminated waste on site and to stabilize mercury. We learned about case studies from BATREC of mercury treatment, transport, and final disposal, including 500 tons of mercury from the Latin American region. We heard about ASGM mercury remediation project in Indonesia, which is fascinating, which is aiming to develop a remediation toolkit which critically must be accessible and affordable for local communities. And so that, I think, pretty much sums up most of the presentations today. And I mean, I think the point of this session was to look at some of the synergies between Stockholm and Minamata. And I think really we touched on a lot of the synergies between Minamata and Basel as well. As far as transport of waste goes, and I think that's one of the some of the overlying themes here today are on reducing mercury supply on the market through treatment, through transport and disposal, managing stocks and decontaminating sites. Now that we have the Minamata Convention, we're starting to ratchet down the use of mercury. And so mercury being an element that can't be destroyed, it needs to be managed in some sort of environmentally sound way. And I think we heard some good examples of that here today. So again, I thank everybody for your time and participation here, and for a really robust, healthy discussion here today.
Thank you, Ben. And then I think with this we'll close today's session. There is some, I'm quite sure there is time to see each other tonight, tomorrow. Yeah, it was a pleasure to host you all, and we'll see each other in the next couple of days. Thank you, Ben.